In this problem, we have a sign with a mass of 100 kilograms, and it is suspended from a pole connected to a socket joint at A, and it is also supported at two cables that go from B to C and B to D. We are asked to determine the tension in those two cables and also the reaction at A. So what I want you to do now is go ahead and pause the video and draw the free body diagram showing applied forces and reactionary forces. Alright, this is the three body diagram I came up with. To note, the reaction at A is, that's a ball joint, so it doesn't support or resist any moments. So the only forces that you're going to have there are X, Y, and Z, okay, components of A. Of course, you have your tension forces going from B to C and B to D, and we can work out their components based on the displacement X, Y, and Z, and come up with the force vector for that. We also have a force of the sign itself, 100 kilograms, which will be 981 newtons, okay, and that is just in the pure K direction, okay, and located 1 meter over from the Z-axis, and it is located on the Y-axis. Alright, so now that we got our free body diagram established, the next thing I want you to do is to break up all the forces. So it's the force reaction at A, the weight of the sign, force BC and BD, and break those up into its Cartesian coordinates. So go ahead and pause the video and just break those up into their I, J, and K. Alright, the results are for force A, we got a unknown AX in the I, AY in the J, and AZ in the K. For the force vector for the weight of the sign, it is just simply negative 981 newtons in K. Now for the force in the tension cable BC, using the displacement, okay, and we also know that the distance from B to C is 3 because we took the square root of the different deltas, the delta X, delta Y, and delta Z. So this works out to its component of 1/3 FBC in the I, negative 2/3 force BC in the J, and 2/3 force BC in the K. For force BD, we get negative 2/3 force BD, negative 2/3 force BD in the J, and 1/3 force BD. Alright, next what I want you to do is use the summation of forces in X, Y, and Z and come up with those three equations. And all we're basically doing are we're going to add up the columns I, J, and K. So go ahead and pause that, then write out those equilibrium equations. Alright, the equilibrium equations for the summation of forces in X is AX plus 1/3 FBC minus 2/3 force BD, and that's set to equal to 0. Summation of force in Y is AY minus 2/3 FBC minus 2/3 force BD is equal to 0, and the summation of forces in Z is AZ minus 981 newtons plus 2/3 force BC plus 2/3 force BD. So looking at these equations, we realize that there's nothing we can directly solve for, so we will then go on and do the equations of equilibrium for moment, and the point we're going to pick here will be the summation of moments at A. Okay, so what I want you to do here is write out the equations of equilibrium for the moments at A, and go ahead and break them up into summation of moments about at A about the X, and then at the Y, and at the Z. Okay, so go ahead and pause the video and write those three equations out. Alright, so we'll first look at X. So the summation of the forces summation of the moments, at A in the x direction, of course, is equal to 0. So let's look at the various forces and how they contribute to a moment. If we look, we'll first look at the weight of the sign. So the weight of the sign is, and these will be forces in the k direction, because the k direction will create that spin around my x-axis. And as long as x, or the k force, is not in line with the x, then it will produce a moment. So we've got, the first one is the sine, which is minus 981. And it's minus because it will create a clockwise motion around the x-axis, and it's located at a distance of 1 meter over. Next, we'll look at the k component for force BC, okay, and it's acting straight down at B, and it has a moment arm of 2. It is pulling up and will create a positive moment, so that's 2/3 FBC, which is the k component, times 2. Next, we have the force BD. Its x component is 1/3 force BD, and it also has a moment arm of 2 meters. Okay, and so that leaves us with 4/3 FBC plus 2/3 FBD is equal to 981. Now we'll jump on to the summation of the moments at A around the y-axis. And let's look at that carefully. So is there a, look at all the forces. So the x, or the weight of the sign, does not create a moment about y because it's in line with it. None of the forces or tension forces create a spinning motion about the y-axis. So the summation of moments, there is no forces, so it's just equal to 0. And again, there is no moments resisted by A because it's a ball and socket joint. Next, we'll look at the summation of moments about the z-axis. Okay, and there we've got the sign does not produce any of those because it's in line with that. It's right on that axis, okay, or in line with it, so it's not producing a moment about the z-axis. But the component forces of FBC, so if we look at FBC, we're looking at the x component of that, okay, and it is actually producing a negative spin around z, that x component. It is going clockwise, and it is at a distance of 2 meters, so it's negative 1/3 FBC, distance of 2. And then the x component in the I direction for force FBD is creating a positive moment, okay, counterclockwise rotation around the z-axis. And that's going to be equal to plus 2/3 FBD times 2. Okay, and we can solve for FBD, and it is equal to, because those are the only terms in there, that's all set to 0. So FBD is equal to 1/2 FBC. We can then take this information and substitute it into my summation of moments around the x at A, and we can directly solve for force FBC, and we get 588.6 newtons. Okay, that's the magnitude in that force, and then by going back and substituting it into the equation that we solve for the summation of moments around the z-axis, we get force BD is equal to 294.3 newtons. Now that we know the tension forces, we can take those numbers, those magnitudes, and input them into our summation of forces around the x and solve directly for AX, and we get AX is actually equal to 0. Then we go to the summation of forces of the y, and we put in our numbers for force BC and force BD, and we get AY is equal to 588.6 newtons, and since it's in a positive direction, we guess correctly, so it's up. And then we make our substitution in the summation of forces in Z, and we get AZ is equal to 490.5 newtons, and also positive, and therefore we had guessed correctly in our free body diagram and assumed them in a positive direction. Now, of course, all these numbers were replaced typically 2, 3 significant figures, but I just wanted to show you the 4 so everyone would have a better idea if there was some rounding errors for you.